This is the last part of the lesson 4, where we present two operating machines, the chiller and the heat pump. We remember the meaning of operating machine. It is a machine where work is given and heat is produced or subtracted, since heat can be positive or negative. Heat pump and chiller have the same thermodynamic cycle, but in a heat pump we are interested in generating heat at higher temperature versus the ambient one, while in the chiller we are interested in subtracting heat at lower temperature than the ambient. Also, if we stay with the thermodynamic rules for heat and work, heat is positive when given to the system and negative if given to the user. For a chiller, we need to maximize the positive heat. For a heat pump, the negative one. And for the technical work, since it is positive when given to the system, we need to minimize it in both cases. The chiller is the first operating machine we want to see in this lesson. The circuit is drawn counterclockwise. Its shape and transformations are very similar to the organic Rankine cycle, just in the opposite way. Let's describe this cycle in the pH chart. The first transformation is the adiabatic compression 1-2. Then we have the isobaric cooling 2-3, the isenthalpic expansion 3-4, and the isobaric heating 4-1. In the picture are represented the four processes of the cycle with the corresponding equipment: compressor, condenser, throttle, evaporator. Moreover, the quantities: superheat, that is the difference of the enthalpy between saturated condition and the compressor entry; subcooling, that is the difference of the enthalpy between saturated conditions and throttle entry; adiabatic drift, the difference of enthalpy between the isentropic and real compression outlet. The definitions in the previous slide are also valid for the heat pumps. Let's consider now as a reference a water-water machine having following performance data: cooling capacity 700 kW, supply return water temperature at the load side 12-7 degrees, supply return water temperature at the source side 30-35 degrees, compressor input 162 kW, EER 4.32, refrigerant R410A, and the compressor type is scroll, 2 units, 2 circuits, 4 compressors in total. In the picture is represented the simplified process schematic. Let's study the circuit under two approaches, always using the real gas model for the refrigerant: the ideal case, where all the transformations are reversible, and the real case, where all the transformations are irreversible, and we need to do some further assumptions. To make it simple, we consider no superheating and no subcooling, and we solve the problem using the tool fly carpet. Being all transformations reversible means that evaporator temperature equals the ambient temperature at 7 degrees, the condenser temperature equals the ambient temperature at 35 degrees, the compression is isentropic, means that the adiabatic efficiency is 1, and if we neglect all the pressure drops, we can generate the diagram pH using the tool fly carpet. The link is in the video comments and also in the slide above the chart. The mass flow is 12,684 kg per hour. The capacity is 700 kW as per input. The compressor work 85.3 kW, and the EER, that is the ratio between the Q at the lower temperature and the work, is 8.21, and since of big deviations versus the real performance, the model 1 is definitely not fitting. For adopting the model 2, we make some assumptions. The delta T between the evaporator and the condenser versus the ambient we set at 5 degrees. The compressor adiabatic efficiency we set at 0.8. In this chart we see some details of the thermodynamic variables per each state. The new process states are represented in the coming slide as well as in the new chart in the diagram pH aside. The mass flow is this time 13,404 kg per hour. The compressor work is 156 kW, and introducing the electrical efficiency eta E 95%, we will see details in the slide 66, we can determine the electrical work as ratio between the technical work and the electrical efficiency. We find 164.2 kW, and the EER this time is 4.26. The results are very close to the real performance. There is still some deviation, and the reasons can be that we have neglected the pressure losses and that we have estimated wrongly the adiabatic efficiency of the compressor. Further details of the thermodynamic variables of the states are represented in this slide. The thermodynamic cycle of the heat pump is exactly the same, but the target is different. Here we are interested to generate heat at higher temperature rather than subtract heat at lower temperature. Let's consider now as a reference an air-water heat pump, Daikin make, having following performance data. Heating capacity 551 kW, supply return water temperature at the load side 45-40 degrees, outside air temperature at the source side 7 degrees, compressor input 163.3 kW, and COP 3.37 as a consequence. We remember that for the heat pump we use COP instead of EER. The refrigerant is R32, the compressor type is scroll, 3 units, 2 circuits, 6 compressors in total. Let's study the circuit under 3 approaches, always using the real gas model for the refrigerant and considering all the transformations irreversible. For sure we need some further assumptions. The first approach is considering a single stage cycle, as we have seen for the chiller at the slide 54. Then we consider a double stage cycle with intercooler, and finally a double stage cycle with economizer. That the transformations are irreversible means that delta T between evaporator and ambient is different than 0. We set negative 10 degrees. Therefore, the temperature at the point 5 will be 7 minus 10 equals negative 3 degrees. The delta T between the condenser and the ambient we set at 5 degrees. So the temperature T4 is 50 degrees equals 45 plus 5. The compressor adiabatic efficiency we set at 0.8. And neglecting all pressure drops, we can generate the pH diagram aside with the tool fly carpet. The mass flow is 6,785.6 kg per hour. The capacity is negative 551 kW as per input. The compressor work is 141.5 kW. The electrical efficiency is 93.3%. We will see details in the slide 66. The electrical work is then the ratio between the work and the electrical efficiency. We find 151.1 kW, and the EER is negative Q over L 3.64. Reasons for deviation can be, as for the chiller case, pressure loss not considered or efficiency overestimated. And here we have also some details about the thermodynamic states. We keep now the same parameters with the addition of an intercooler. The outlet temperature will be 25 degrees and the corresponding pressure 15.2 bar. Neglecting all the pressure drops, we can generate the diagram pH and we find following data. The mass flow is 7,614 kg per hour, the capacity negative 551 kW as per the input, and the compressor work is now made of two steps, the steps 1-2 and the steps 3-4. The corresponding work is 150 kW. If we introduce electrical efficiency of the compressor, the real work is 160.7 kW and the EER is 3.42. This solution is definitely worsening the performance and we cannot use for the heat pump. It could be used for the chillers. In this slide we see some details of the thermodynamic states as well as a schematic of the process with the corresponding numbers matching the diagram once. In the last example, we keep the same parameters as before with the addition of an economizer, and to find the economizer conditions we set a delta temperature between the states 9 and 7 to 5 degrees. Neglecting all pressure drops, we generate the new diagram pH and we find the following data. The low pressure mass flow is 5,639 kg per hour, the high pressure mass flow 6,930 kg per hour, the capacity stays the same as per definition, and the compressor work is split into two steps, but every step has a different mass flow. As calculated above, we land to 132 kW, and introducing the electrical efficiency, this value should be corrected into 141.5 kW. Finally, the EER is negative Q over L 3.89. We demonstrate that this solution is increasing the performance. Here we have some details of the thermodynamic states, a schematic with the same numbers as used in the pH chart. In this table we collect the electric motor's efficiency per different efficiency class and power output. We have evidenced the ones used in our examples. Here are resumed the formulas used in the lesson 4 for completion, retrieval and further use. I hope you have enjoyed this video. See you in the next presentations. Bye bye.